The broadcast is now starting. All attendees are in listen-only mode.
Well, good morning, good afternoon, good evening, good night, whatever time it is for you folks. We have about 100 people here with us, and we will be joined by another 100 people who are going to be late, I'm sure, in the next few minutes. So we have our friend from Australia. You can see the face, I think, and I'm here from the United States. My name is Krishna Vedula, and what I'm going to do very quickly is show you what we're trying to do here is something that's quite interesting, that we are trying to connect the world in terms of the challenge that we have. And I'm just quickly going to move in and see if I can. Oops. Oh, sorry, I should have done this beforehand. But anyway, what can I do? Okay, sorry guys. Okay, this is what we're trying to do here. Okay, we're trying to build a community of people who are willing to address this challenge. So I represent IFES, GEDC, and IUC. I've got Hans Hoyer here, who directly represents IFES and GEDC. He will join us in just a minute. But the idea is that we are facing a challenge, right? And this challenge, we are trying to address this challenge by communicating online. Most of us are in lockdown mode all over the world. And I think it's important that we have a global community of online learning, for doing online teaching. So that's the whole idea here, and we are glad to have our first webinar on this for this community, and we hope all of you will join this community and continue to be part of it. First webinar is from Australia, and what we have here is let's see. I'm going to go back and let me see what the this technology always something that we have to learn how to use, right? That's the right buttons. Yes. And okay, and then let's see. People can see me, but I'm struggling to get out of this mode here. Let's see. There we go. And I'm going to put on this screen here. Okay, so here is our today we have Alfred Bresnik and Carlo Manfredini and Shinoj from Emona Teams Australia. They will be talking to us on online engineering education for electronics and telecoms, multi-user remotely controlled hardware experiments. Okay, so with that, I'm going to hand you over to Carlo, to Alfred rather, and we'll make him the presenter, and we are ready to go. Okay, Carlo, click show my screen. I mean, not Carlo, Alfred, click show my screen.
Yep.
Yes, perfect. All right, so and you could turn off your video so that people will focus on what you're trying to say. All right.
Excellent. So you can see my
Yes.
screen, okay?
Yes, please go ahead.
Brilliant. Well, look, good morning, good afternoon, and good evening. As Krishna said, my name is Alfred Bresnik from a company, Emona Instruments, based in Sydney, Australia. Look, in the next 30 minutes or so, I'll give you a detailed description and some insights into what you may not have seen before, a new mode of hands-on engineering experiments for students, and that is multi-user remote controlled labs. So I'll just also have, excellent. Yep. Now it's working. So in this presentation, I'll show you how you can enhance your lab program with remote access 24/7 hands-on labs. So as I said, our company is Emona Instruments, located in Sydney, Australia, where I'm talking from, and it's just after 9 p.m. on Monday evening here. So our company has for some 30 years been manufacturing some very specialized signals and telecommunications lab teaching equipment, as well as these multi-user remote control labs. These labs are not actually, what I'll show you tonight or today is not something that's just come up recently. Our company was approached actually in 2004 by a major US university syndicate, and they wanted to implement distance labs. Our reply was, why don't you just use simulators? They'd be a lot cheaper than remote controlled hardware. And we were advised no. They had access to the best simulators in the world, but what they really wanted for their beginning, for their early students who didn't have experience, was they wanted the students to see, quote, noise, crosstalk, distortion. They wanted to see real signals rather than just idealized simulations which they were already using. So what you'll see today is a result of many years of development of these remote controlled labs. So I'll describe and demonstrate how a single piece of hardware allows you to enhance your electronic circuits and telecoms lab programs by providing a range of hands-on experiments that can be controlled across the internet by typically 30 students or more simultaneously. So let's first look at, what does remote labs mean? It means controlling real circuits in a way not too different from how scientists control spacecraft across the universe, or engineers control plant and equipment from their control desk in the factory. So where do these remote labs fit into this engineering labs experience? We've seen that remote labs provide a third alternative to the traditional hardware, hands-on labs, and the on-screen simulation experience. So described as open, flexible, and cost-effective, remote labs are a tool that you may not have seen before. Lab equipment is called netCIRCUITlabs for electronic circuits experiments and netTIMS for telecommunications experiments. Normally referred to as distance or remote labs, the motivation for these labs is foremost to enhance the experiential learning and understanding for the engineering students. We see today growing interest around the world in remote control labs sparked due to this current worldwide health crisis. However, interest in remote labs has been around for many years. Some countries it's been there because of the open university format courses where students cannot or do not get to the campus. In other countries, there's been a growing interest in remote labs because there are just too many engineering students enrolled, given the physical constraints of lab space, staff, and time. Real examples of this are in China, where we know our remote labs are being used in courses at one university with 800 students, and at another university, 1,200 students. And just to put some meaning to that, the 800 students are at Shandong University, where students are divided into various groups. The 1,200 students are at Nanjing University of Technology, where they actually have quite large groups of students accessing this one piece of hardware. Another interesting point, especially something I've seen in India, is that in some countries, there's a new application for remote labs called active learning, where the remote labs are used during the lecture, where the professor asks the students to log on and try out what is actually being taught. To introduce remote labs, let's first define them with respect to traditional hardware labs. In electrical engineering labs, experiments may involve trainers with predefined circuit boards, or the student may build electronic circuits on a breadboard. These can be located in a lab on the campus using traditional test equipment or virtual instruments like NI-Elvis, or can be located at home using solderless breadboards and virtual instruments like MyDAC or Analog Discovery. But what happens if it would be of educational value for the students to carry out more experiments, but they can't attend the campus, or there's no further lab space or time or staff available, or the breadboard circuits become too complex? This is where remote labs come to the fore. So here we can see, like traditional hardware labs, remote labs may offer both predefined, pre-wired experiment circuits, or they can offer breadboard style experiments where the student actually wires and patches together the experiment in real time. And this is something that I'll demonstrate in about 10 minutes or so. Remote labs are a direct extension of the physical labs because remote labs are real hardware. There's no setup for the student. Just launch an internet browser, log on, little different from sitting in front of a breadboard or trainer. Remote lab attributes. So remote labs respond fast, make a change, and the test instrument response is almost instantaneous, just like the traditional experiment. In remote labs, the components and circuits are real rather than ideal. So the student sees real-world phenomena like tolerance effects, noise, crosstalk, distortion, aliasing, and the like. Remote labs function identically to what a student has already seen in a traditional lab experience. So the transition from a traditional lab to a remote lab is a seamless follow-on. There's no multi-level setup menus, syntax, protocols, or complex parameter menus, which might appear and confound the learning experience for the inexperienced student. There's also no run-stop button to wait for the compilation to view a waveform. Once exposed to a remote lab, the student will feel the similarity with the traditional lab equipment, but they are controlling real hardware remotely. So let me reiterate what is meant by remote hardware labs. I'm referring to traditional hands-on lab equipment with knobs and switches and connections, which can be fully remotely controlled. By remotely, I mean via browser-based graphical interface with actual physical equipment communicating to the browser via the internet. Here is an example of a student's browser control window. Note that the function generator is at the top left, the oscilloscope controls are in the bottom half of the screen. In this transistor circuit example, the student has real-time experiment control of circuit components like switches and potentiometers, and of course, multiple oscilloscope viewing points across the circuit. Note the live waveform display on the oscilloscope. I just need to point out, these are real signals, not simulations. Access can be either local, within the same lab, all campus, or across the city, or across the country. In order for a remote lab to be practical and economical, they need to cater to multiple students at the same time. Utilizing very fast time-sharing technology, one piece of hardware lab equipment has the possibility to be, in effect, a multi-user system. From our experience, this type of equipment, a remote lab unit, can easily service 30 students at the same time, independently and transparently, 24 hours a day, 7 days a week. So now we can think of the remote lab methodology as a multi-user hardware platform with little setup, practically no maintenance, very little inventory. Just plug the control unit into the LAN, allocate an IP address, obviously set up your router, and let the students log on. Student access can be controlled by an easily uploaded enrollment database, and student activity can be monitored for time of access and recorded for confirmation of activities carried out. The professor or administrator can access the simple summary of utilization or delve more deeply into granular utilization information. Some recent examples of feedback from professors using these remote labs. For example, Professor receives a report submitted by a student which looks suspicious. Professor can access the student utilization summary and instantly see if the student actually logged on, when, their IP address, for how long, and whether there was any activity associated with their session. In just the last few months, we've had different professors, one from Australia and one from China, commenting how they are able to instantly fail students who submitted reports where the professor could see that there was no evidence of the student having done any work at all. Obviously, they used Photoshop to copy screen images, but the system captures what they're actually doing. On a lighter note, a professor a while ago told us how he found it informative to review the utilization pages to see how many students actually logged in at midnight the night before an assignment was due that morning. An important aspect to consider when using a remote system is the student must believe that they are actually controlling the hardware unit themselves. To achieve this confidence, a webcam is set up to show the unit with an external oscilloscope connected, say, to some test points, so the student can see on that oscilloscope, not for measurement purposes, but just can actually see waveforms changing as different students use that piece of hardware. This webcam image shows some of the netCIRCUITlabs units located in our Sydney offices, which I'll be demonstrating to you shortly. Another important confidence building tool built into the netCIRCUITlabs system is called Watch Mode. Watch Mode enables individual students working remotely from each other to view the client screen of another netCIRCUITlabs user in real time. This viewing is known as watching the other person's experiment. This enables collaboration and tutoring at a distance, as a student may watch the experiment screen of a professor, or students can watch the screen of another student for group collaboration. Watch Mode implements one actor, many viewers topology, and there is no limit to the number of viewers of the one actor. For example, professor or the lead student. This collaboration can be enhanced with audio discussion carried out via the internet, various internet-based audio services, even such as the one we're using now. This is what netCIRCUITlabs system looks like, a hardware control unit with one experiment board plugged into the control unit. There is a choice of 5 different experiment boards, which we'll look at in the next slides, but only one experiment board is plugged in at any one time. Setup is a simple two-step process. Get a fixed IP address from the IT department, enter it into the admin page, upload the class list, tell the students their experiment's IP address, and they're ready to go. So there's no programming, no programs to download, no syntax, no installation. The remote lab includes the control unit and the experiment board. Emona offers the following 5 boards. So now I'll switch screens between the experiment boards and the actual use of the experiment board. So this first experiment board is for circuit theory, for experiments covering Norton, Thevenin, resistor networks, RC, RL, RLC networks, and so on. This board implements the breadboard style of experiments I mentioned, where the student selects electronic parts and wires them together on screen. The connections made on screen are exactly electrically implemented remotely on that circuit board. Yes, the links and connections the student makes on screen are made remotely on that experiment board. So now let me switch to the actual system. So here is the webcam, live webcam of 4 netCIRCUITlabs units at the Sydney offices. That large grey building you saw, this is in the basement of the building. And the first experiment we'll look at is that unit that you can just see a little bit of the orange board on the bottom right-hand side. So we log on, we enter the IP address, and this is now the home page of that netCIRCUITlabs unit. And you can see the current board attached is circuit theory. The student logs on by username and password. And when they do, they have here, I have a preloaded experiment, but I can say, for example, I can say empty rack. So now I have nothing. I can click here and select the function generator. Let me set the oscilloscope. I'll connect the oscilloscope to the function generator. I'll create sine wave of some frequency. I'll select the time base. So here I can see function generator waveform. So everything I'm doing is real time. I'm not sure how fast your updates, but the update on my screen is about 1 second. So now let me select some resistors. I'll patch the output of the function generator to this resistor. I'll patch another oscilloscope output to the output of the resistor. So these connections I'm making are actually real connections being made on that orange red board that you saw. I'll now select some capacitors and I'll connect capacitor to that resistor, and now we can see immediately the effect. If I change the capacitor value from 100 nanofarads to 1 nanofarad, we see the effect. I reconnect the 100 nanofarad capacitor. So this is what I meant earlier when I was talking about breadboard style experiment boards, where the student actually has elements, has components, and wires them on screen. Now, I am one user. There can be 30 or more users using this same unit, using this same board at the same time, but each user will be running a completely different experiment. For more complex experiments, as I showed you before, when we first logged on, here's a second order RLC. I can set where we're looking actually at the step function of this RLC. So I'll set the time base. And here I can see, here you can see the step response of this RLC. Let me change the capacitor value. And there you can see the immediate effect. Now I'll switch back. Notice here on the right-hand side, there's a breadboard section. This has a very specific function. Let me switch back and I'll select user functions. That breadboard selection allows the professor to build 2 mystery circuits. They can be active, passive, R, RL, RLC, and the student at the end of the course can be asked to, using the test instruments, function generators, oscilloscope, spectrum analyzer, and so on, use those and derive what is the transfer function, what is actually implemented in H1 or H2 user function, which was actually implemented here on this breadboard by the professor. So, as you can imagine, the student can't see what was implemented on that breadboard, so that's why they have to use the knowledge they've gained in the circuit theory course to implement that. Let's move on to a second experiment board. This one is transistors, transistor circuits. So here we can see a selection of pre-built transistor circuits. With this board, 13 different transistor circuit experiments can be implemented. Now I'll switch very quickly to what does the control look like. So this is what it looks like. So this happens to be a 2-stage amplifier. If I click on load, you can see the different circuits that are implemented. We can move the test points around the circuit and we can control switches, and we can control potentiometers and obviously make measurements. The third experiment board we'll quickly look at is op-amps. So op-amp experiment boards implements some 16 pre-wired op-amp circuits where the student again has control over various parameters, switches and potentiometers, function generators, signal sources, and so on. If I go to, here is a integrator differentiator experiment. If I switch on, click on load, you can see the selection of predefined op-amp circuits covered. So here I can change the offset, and you can see the offset on the output integrator moving. Next, digital logic, where here we use an FPGA to implement a large array of different logic gates and counters and state machines. So the student will, if I switch, I'll show you. The student here, you can see I've built a D flip-flop using NAND gates. And here I've got it on the right-hand side, I have a D flip-flop, so we can actually compare the operation of the D flip-flop that I built with gates compared with an actual D flip-flop itself. If we click on select, we can see the range of gates. But it's also important to note, if I select dual AND module, these are all the AND gates available. This is not like a simulator where I can select another set of AND gates, because this is real hardware. These are the only AND gates available to me, or these are the only dual NAND gates available. So this is real hardware being patched in real time. Let me switch to the next, and the last of our current circuit boards is called a build your own circuits board. Now, if the professor has a specific analog or digital electronic circuit required for their course or curriculum, which aren't implemented on our transistors or op-amps or circuit or logic boards, then a professor can actually build the circuit on this board, use the remotely controlled potentiometers and switches which we provide, and thus implement almost any circuit they require for their experiments. Obviously, we provide function generator for outputs, multiple oscilloscope points. So setting up for the professor is actually very straightforward. There's no programming and no syntax involved. Step one, the professor builds the electronic circuit on the breadboard using the power supplies, the potentiometers and switches that we offer. Professor then uploads an image file, which is a simple PNG file, which can be either, as you'll see, in our case, hand-drawn, or can be a neat schematic capture image. The third step is professor then moves the knobs and switches, the remote control knobs and switches around that schematic so that they are near the actual schematic of the potentiometer or switch in the circuit, so that there's, so that the student can easily control that. So let me switch to, there are, if I click on load, you see there's a selection of demo circuits available on this board. What I thought I'd show you is the really extremely famous 555 IC. So here you can see a switch, which is switching between a 10 nanofarad and 100 nanofarad capacitor. So as I switch between the two, you can see the response changing. And then this potentiometer, as I move this potentiometer RV7, you can see the response in real time. So here are examples of what I've just shown you of the students' display on their computer. Note, there's no software to download, only an IP address and a browser to use to have real control and to see real live signals in real time. Here's just a quick glimpse, not meant for reading, but just to give you an overview of the different experiment manuals, the lab manuals that we provide with these experiment boards. The first few are just a lab manual title page for the op amps and the contents page. Second is title page of an experiment and the inside listing of prerequisites and equipment required. Then you'll see we always provide information such as obviously the schematic diagram, but also a zoom photo of the actual PCB so the student can see what does the circuit that they are controlling look like. And finally, a couple of example student experiment pages showing where students need to draw graphs, write answers, record measurements, and so on. The recapping, this is the electronics circuits side. We have shown you one piece of hardware equipment that at least 30 students can use simultaneously. That equipment is available 24 hours a day, 7 days a week, 365 days a year. And it obviously represents an enormous cost saving and an efficiency for the department. Everything I've shown you is available to all of you to try out at any time. And I'll show you access. If you go to the Emona website, emona-teams.com, click on menu, see products, IoT-based hardware, and what we've just looked at are the netCIRCUITlabs products. So if we click that, we get to netCIRCUITlabs, go to live experiments, and you'll see build your own circuits, which I just showed you, op amps, transistor circuits, digital logic, and if I scroll down, circuit theory. So everything I've shown you, I would encourage you to log on and try. Obviously, you need a username and password, and there it's written. The username for all our demonstration units is user, and the password is visitor. So there's an overview. So that covers the electronics experiments, remote electronics experiment side. We can take a 30-second pause. In the next 5 minutes or so, I'll quickly run through our signals and systems and communications systems experiments. Also remote, and these were the actual original remote labs that were developed by Emona. So Emona offers 2 models of remote-controlled experiments for communications and signals theory. One is netTIMS, which provides an almost infinitely expandable range of experiments from signals and systems, the basic analog and digital modulation coding, through to advanced digital modulation schemes as implemented in wireless 4G and 5G systems. And secondly, we have netTIMS FreeWire, which is a compact zero setup system with an optimum selection of 22 building blocks, which will allow some 40 fundamental analog and digital modulation experiments to be implemented by the student. So quick overview of these two. This is what netTIMS looks like. netTIMS is a system, as I said, infinitely expandable, where the professor actually patches together, builds the experiments, but the student then has full control of the experiment. What does it mean by experiment? This is our teaching principle. netTIMS follows the TIMS telecommunications teaching principle, bringing the mathematical equations, which are represented as block diagrams, bringing those block diagrams to life. Because where there's a block in the block diagram, we actually have a real hardware functional block. So if there's a multiplier block in the block diagram, we have a real electronic multiplier, not DSP, not simulation, but real electrical building blocks. So the student can see the experiment theory coming to life. On the one hand, they can look at simulation, and then they can look at the real signals and then contrast between the two. So here in this slide, just briefly, an overview of the topics that netTIMS can cover, from signals and systems, analog modulation, digital modulation, 4G, 5G, wireless theory schemes, even fiber optics, as well as software-defined radio implementations. And again, just to emphasize, this is a multi-user system where the student logs on by username and password, and then they have control. And here you can see the student's display. What does that display mean? This. When a student sees a module in the far left-hand slot, there is actually a real electronic building block in the netTIMS hardware in that exact position. When there's a module in the third slot, it correlates to the screen. So there's a one-to-one relationship between the two. Let me quickly show you what netTIMS looks like. So here, just briefly, we actually have a long pseudo-random sequence being clocked quickly and passing through this tunable low-pass filter. So the red waveform you see, I switch off the time domain. There's the time domain, frequency domain. So as I tune this filter, you'll see the bandwidth of the noise coming out changing. So low bandwidth, below 3 dB point, moving it to the maximum. So there you can see a simple illustration. The rest of this experiment is actually a second order IIR filter, which I won't go into now, but you can in your own time log on to this experiment and try it yourself. Lastly is the netTIMS free wire system. So this is a different level. This is the build your own, where the student builds the experiment as they go, because we provide a selection of building blocks. So the student selects the blocks, patches them together, and then can see the real waveforms. But remember, there are 30 or more students logged on to FreeWire at one time, and all the students can be implementing the same experiment. All students can be implementing different experiments. The system doesn't care. Each student has a completely unique session. So I can quickly switch to, so here I've logged on to netTIMS FreeWire, and if I select, let's say, master signals, which allows me to look at, let's say, let me just clean this. So there's a 2 kilohertz sine wave. If I look at a 100 kilohertz wave, let me select a multiplier. So I'll connect 100 kilohertz to one input of the multiplier. I'll connect 2 kilohertz to the other input of the multiplier. I'll connect channel C to the output, and we expect to see 2 kilohertz multiplied with 100 kilohertz, which is double sideband suppressed carrier. So there you can see in NetIM's FreeWire, I selected 2 blocks, I patched them up in real time, and I saw the instantaneous response. I can look at the spectrum, and obviously I'll see an upper sideband and a lower sideband signal. So again, if you go to our Emona-tims.com website, you can try these systems out as well. So with that, I conclude our presentation. So I hope I didn't go too fast, but I did want to actually demonstrate what I was talking about rather than just claiming that we can do so many things.
What impressive, very impressive presentation, Alfred. Thank you so much. We are open to questions. Text them. I think best to text them because we have 150 people here, so we cannot unmute anybody. Just text them. In the meantime, if Carlo or Shinoj wants to say anything, please come in. Actually, Doru is also here, or Sut from Europe is here.
Yes.
You know Doru? Oh, okay. He has said
yes.
about you.
Hello.
So Doru,
hello.
you
Good
want
morning,
to say
Doru.
hello? Doru, you can unmute yourself and say hello if you want. I've made you a panelist.
Hello. Hello
Yes.
from Russia, from Romania. Also 2 students from Ukraine who came to understand the NILV's technologies. Look at your presentation. Thank you very much for wonderful presentation.
Thank you, Doru.
Thank you.
Okay, so I've got a few questions coming in. In the meantime, if Carlo or Shinoj wants to join, that's fine. Otherwise, okay, the questions coming in, keep the questions coming in. What is the chance of a circuit failure due to incorrect user circuit diagram?
Well, since it's a completely controlled environment, there cannot be any circuit failures. Where students can actually build their own circuits using our elements, remember that we have designed this for student learning. So a student can connect any point to any point, and nothing will smoke, nothing will overheat. This is designed for student learning, and it assumes the students make mistakes.
Is there any example of wireless communication experiments on your system?
Wireless communications means what? Means top modulation schemes such as OFDM or spread spectrum and so on. And yes, of course, we have experiments we have an array of experiments in those areas.
Okay, that was from Single from India. Okay, Mahesh from India says, what was the first question? Okay, what's your, I guess this is, if you have more than 30 students, what happens? 60 students.
Okay, look, we like to be conservative and say we would recommend 30 or so students, but real data, real information is, for example, from Nanjing University of Technology, where they have 1,200 students uploaded to one of these netCIRCUITlabs, and they explain their course goes for 20 weeks. They have 6 to 8 experiments per semester, and they personally find the optimum for them, the optimum number of students in their program, because they have so many of them, is around 70 students. So they give their students a 3 to 4 hour window across the week to do the experiments. So to answer specifically what happens, this system is real. So statistically, if a lot of students all change a parameter at one point, then the system will queue. So so if there are many students all using the system absolutely simultaneously, then instead of having an instantaneous update, it might take 1 or 2 seconds. In fact, at Shandong University, when I asked how do they cope with this, having 800 students, the professor tells the students quite bluntly, Oh, look, if the response is too slow, don't worry, log off and come back later. So look, so these are real examples. These aren't thought experiments.
Carlo, you want to say something? Go ahead.
Yes, thanks very much, Alfred, for a lovely presentation. I'd like to also add, I'm Carlo from Emona, R&D Director. In the administration section of the server, there's a lot of statistics on the performance of the server. So the administrator of the unit can have a look and see how many students are logging and how many seconds each one is getting. And if it turns out that there are too many students using it, they can easily control access to the server to spread out the students, or perhaps even get a second server if necessary. So the system is adaptable and quite elastic to meet demand. It's scalable. It's perfectly scalable to meet your demand. Thank you.
Okay, another question has to do with the monitoring of the students. How do you monitor the students? I'm not sure what the question means, but
I'll just continue there. So the administration page of the server has a student database. So you simply load a spreadsheet of the students who are allowed to access the system. Now that's how you control student access. How you monitor them is every one of those students, every time they click and interact with the GUI, their activity, their amount of clicking is graphically logged in the system. So at the end of a session or at the end of a semester, you can download the activity profile of each student and look at it on a graph or a spreadsheet. So what we do is we monitor the amount of clicking. We don't monitor more than that because that would be a waste of time. Nobody's going to ever look at that. I hope that answers your question.
Yeah, thanks. Another question was, how do we interact with the students? Are they on their own? Are the faculty interacting with them? What's the how does that work? Do they have any questions while they're doing the experiments?
Because there are so many platforms for communicating and chatting, we leave that to the customer to decide which platform they want to use to chat amongst themselves using internet tools, whether it's Zoom or Skype or some kind of web chat. The other form of interaction is watch mode, where you can look at what each other is doing. And I'd like to also add, some professors are concerned that that might lead to cheating amongst students. Mm-hmm. In the administration section, you can simply disable watch mode so that students all have to do their own independent session with no collaboration. It's completely under your control. Thank you.
Yeah, thank you. We have Vincent Olema from Uganda saying this is an excellent presentation. Thank you. I've always wanted to set up system like this at our institutions in Uganda because most colleges do not have equipment. What can it take to me to start something like this in Uganda?
Alfred,
as we said, the system is extraordinarily simple to set up. You take it out of the box, you plug it into the power, you plug in a crossover cable, you set up, and with that on your laptop, you set up the IP addresses, upload your student list, and you go. So it's really important to know that there's nothing required in terms of what computer resources do I need. Do I need fast internet? No, this system was designed when the internet was very much slower. So it uses extremely efficient communications between the client and the netCIRCUITlabs or the netTIMS system. So that's why we can implement such fast time sharing, and that's why even in environments where the internet may not be very strong and very fast, our systems are designed to operate in environments like that. So you don't need to set up super fast internet. You don't need to set up enormous resources to establish a remote lab like this. And the other alternative is, of course, if you're not doing it on the internet, you can set up a lab. And this, again, we've seen around the world, where instead of buying 30 pieces of equipment, there's one netCIRCUITlabs or one netTIMS in a lab, which is just within the LAN of that lab. and the students log on and use the system. So the system's really quite adaptable.
And I'd like to add that basically, even if you have an internet connection of say 1 megabit per second, which is very, very slow, you can use our systems perfectly adequately.
Question from Lebanese American University, Ahab Shaya, wonderful presentation. There anything like this in electric machines lab and high power labs?
No.
I'd just like to add, given that this is is letting students use real equipment and time sharing, it's not possible for multiple students to time share real machines in real time simultaneously. So no, we have not addressed that issue.
Question from Kuwait, from Wakar Zafar. Students should only use desktop or laptops, or can they use just their phones?
The system's designed to operate in HTML5 browsers, so they can use tablets. I wouldn't recommend using your phone. It's a little bit on the small side. It's possible, but a tablet is perfectly fine.
Hans, you want to jump in there?
I do. Thank you. Krishna, can you hear me?
Yeah.
Yeah, thank you very much. Dear Alfred and Carlo, I want to deeply thank both of you on behalf of the IFES and GDC communities during this very, very difficult time that we want to do all that we can to continue to connect in a positive, meaningful way our global community. So this presentation that you've given sets that tone, as this is our first one. And we are in conversation with good colleagues in Sharjah, in China, and other places to follow up with other webinars. I thank you kindly, both of you gentlemen, for your very thoughtful work. And all the best to all of you participating in our webinar today. Thank you very much, Krishna.
Let me just quickly do a quick poll here. I just had a couple of polls, and I had a lot of people asking me questions about connectivity here. So I'm just launching a poll. Can you hear and see? Can you hear? No, I cannot hear or see. I mean, I guess those are left. I actually can hear and see, I assume, right? Just keep send me what you can. Okay. Respond to this poll, because I'm just curious how many of you are having problems. Because when you first came on, several of you had difficulty. We still have 150 people with us, and I can see that that there's 1% of you saying you cannot hear or see, 7% says you can hear, and 92% says you can see and hear, and that's most of you have voted by now. So yeah, I apologize. I regret some of you cannot hear and see, but this is how it is, I guess, the internet and so on, and your location and other places. I'm glad to see 90% of you can both see and hear. Thank you for that. What we are trying to do here is maybe we can have a little discussion here on a couple of things. I'm going to close this and share just for you to see the results of the and this is a feature that we can use on this program with the webinars, where we have these kinds of interactions. It's not completely passive. It's not just one way. As you can see, we have had a lot of questions and texting and conversations. So we can make online education actually quite interactive, contrary to what sometimes people say, that we can't do that. But I think it can be done, and I'm going to hide that. And maybe what I would like to see is this effort, this fantastic webinar by Tim Emona to lead to a more global community of learning. So I'm just I'm just going to pop up another quick question, and we can have a little discussion here. We'd like to build a community here. Now, this is the whole idea is not just one webinar, but a series of webinars, maybe 1, 2, or 3 every week for the next several weeks, or for a long period of time. We are hoping that many of you in this group will be part of this community, and depending on your specific interest, you may or may not join certain different into every webinar. But perhaps once a month or so, we will have a common meeting the community and just share ideas. Talk with each other and say, okay, this was good, this was not that useful, this was useful. Can we find somebody to do this, somebody to do that, and help us build this community? Because I see that the 93% of you said yes, and 7% said not sure. Nobody said no, so that's good. So I'm just going to show that. So we are a community. We all have the common challenge that we face around the world. But let's work together. Let's hold hands and work together to build this community further. And in order to make that happen, we need help from each one of you. Okay, we want you all to think back to all your connections, your network. I can see that we have people from all over the world here. One professor from Uganda, unfortunately, just emailed me just now saying that sorry, you cannot join. This is that young professor that Hans, you know very well, in Uganda. She says cannot join because the software is not available. The GoToMeeting not available in Uganda. But I see that other people have joined from various other places. So sorry, that's Sudan. Sudan was that professor from Sudan. But I can see that, as you can see, we got people from all over the world that have joined, and we have picked this time because of the time zones, and we have another version of it. I mean, I repeat this again at in several hours after Alfred and Carlo go to sleep and get up in the morning in Australia. They'll go to sleep, get up in the morning, Australia, 7 o'clock in the morning, they'll be up again. And they will have another group of people who are mostly on the west coast of Western Hemisphere who will join us. And so help us identify people, who can give these kinds of webinars. Alfred, in particular, I think you have mentioned that there are several people in China who have used your equipment. Maybe some of them might be willing to come and share their experiences with us, particularly because we're talking about hundreds of students together simultaneously using online programs and learning. And this is something that would be useful in places like India, places like other places with large populations and large number of students, and then people from the United States, and so I mean, it's a challenge that's out there, but it's exciting for us who have to try to find innovative solutions to address this. So we have a minute left, and we'll let whoever wants to talk, Alfred, Carlo, Sinoj, Hans, or Doru, anybody wants to make some quick comments as we wind up.
Look, I think I'd just like to quickly say thank you very much to you and to Hans for this opportunity, just to show another solution for helping teach engineering students their craft and what's important. So this is one of many solutions. Thank you for the opportunity.
Okay, this is being recorded, by the way, so the recording will be available, and it will be we will try to mail it out, the recording to all of you, but just give us a little time to do that. I guess other than that, I think Hans, you can have the last word if you want.
I think the powerful statement you made in terms of us globally holding our hands together, I think that's powerful. Let us work together in a way globally we may not have in the past. Build on this first wonderful experience and take it much further. Many, many thanks, Krishna, and all of you.
Actually, physically, we cannot hold our hands because of the distance separation we need to have.
Exactly.
Virtually, we can hold our hands.
Absolutely. Absolutely.
So we have 150 people that were here holding hands together today. Let's all work together. Thank you all, and God bless.
Thank you, Krishna.
Thank you,
Thank you,
Krishna.
Hans.
Bye-bye.
Wonderful.
Thank you.
All the
Bye-bye.
best.
Peace be.